we solve using an ODE equation, and then further solve all the equation using the integration method. Okay, so week 2, we are going to use another method of modeling, input-output modeling, using the transfer function. So transfer function is a method to derive an equation to represent the process you want, the output, the relationship between the output and the input, using the conservation of law. So we have 3 conservation of law in this module. We have mass balance. So with the parameters given to you, you have to get the mass balance, rate of the mass, which is the, for example, kg over the time. And then we have the composition, or we call as the component balance. So this is like the mass balance, but we multiply with the composition, the equation. Then the third one will be like, if the temperature is not constant, then you have to consider the energy balance. Okay, then it will involve the one like you have learned, conduction, convection, like the one you have learned in the previous module, which is the thermodynamics and heat transfer. Okay, so we also have included few examples in this topic, lecture 2. So we have the mercury thermometer. So we have the output, which is the reading of the thermometer. Then the input will be the surrounding temperature. We have the mixing process like the previous week 1. But week 1, we solve using the integration method. Week 2, we are going to solve everything using the transfer function method. Okay, so you'll be having unsteady state balance minus the steady state balance. So we'll be having few examples to let you practice how to solve the transfer, how to solve a modeling of a process using the second method, which is the transfer function. Then we will be including more examples in the tutorial 2. Okay, then you will actually learn the linearization, meaning that what if the parameter that you want, for example, you study the level of the tank. Level is your control variable or is your output. So the ODE equation, the level, we use the, for example, the variable of H. So the H, it is not power to 1. So if let's say the variable you want to study, it is not power to 1, then you have to perform linearization. So you have learned this linearization last time in one of your maths. So we have this, I think, linear Taylor series expansion. So this one you have learned in your maths. So we'll be using, or we will do a brief recap. So later I will show you what will be, how to solve this. If let's say your output, for example, level H, or your output is temperature T, it is not power to 1, then you have to make this output power to 1 using the linearization method. Okay, so then mathematical models for system. So this is the introduction. Suppose it is the same like the week 1. Why we need to derive the equation to represent the process? Because the model or the equation allow us to investigate how a system will react dynamically, meaning that, for example, you want to study the variable of temperature, so versus the time. So this is the dynamic model. The value of the temperature will not be constant. It will change according to time. So we are going to get this equation first week using the integration method. Second week using the transfer function method. So how the system will react, follow the time versus the time. To changes imposed, for example, you change one of the input, like the previous week, they change the input from one value to the other value. There can be multiple inputs to the system. So due to the change of the input to the system, then you will get the dynamic model. If everything remains constant, no change, meaning that the system achieves a steady state, they will be no dynamic model. So as long as there is a change imposed to the system, then you will be deriving a mathematical model, which is a dynamic model. It will change according to time. Okay, so later on, few more weeks, you actually will link these. The process you are going to derive now is actually the transfer function block for the process, which is the GP. So we'll be having a controller transfer function. We'll be having the valve control transfer function, the pump transfer function, maybe the sensors transfer function. So one of the block diagram or transfer function is actually the process. Like for example, you want to control the tank level. You want to control the temperature of the mixing tank, of the CSDR, of a heat exchanger. So this is the process. So P stands for the process. GP, G stand for the transfer function. So P means transfer function of the process. So you are going to derive the transfer function of a process using the method of transfer function. So we will look mainly at linear system at the beginning. Then we'll be having one non-linear example at the back, where you have to apply the equation of Taylor series expansion to change or to convert the power not to 1 into power to 1, means linear. If linear means the parameter you are going to study must be power to 1. Okay, so input-output modeling, meaning that you have output over the input as your transfer function. So from here, for example, you have a process model. Input means anything will affect your output, and you apply a change to your input so that you will get the equation to represent the output over the input. So the one you have no control on it will be the disturbance. So the disturbance also is categorized as one of the input to the outputs. Just you can manipulate the input of this, we call as the MV. Wait a while, I need to my iPad connecting. What happened?
Give me some time. Later remind me to record the session. Drop already the line. Share screen. Okay. Okay. Record. Not like totally drop, disconnect. Okay, continue. Okay, so from here, just now where am I? So we have two inputs. So the one we can change, can manipulate, can vary is the one we call as the manipulated variable, MV. The one we cannot change, but it is still the input that will affect the output, we call as the disturbance. So we have three process variables. One is the control variable, CV, or we call the output. The other one will be the manipulated variable, and then the disturbance. So system can be very complex. That's why we simplify the process with assumption. Like for example, no heat loss to the surrounding. There is no convection, for example. So you will have a lot of assumptions to simplify the model. Okay, variable groups, for example, inputs, anything that affect the system or acted upon by the system, like we have the manipulated variable and we have the disturbance variable. So these two are the input. Output variables will be this, which is the one you want to control. For example, you want to study on the temperature change. You want to study on the composition change. So this one will be the dependent variable, result from the system action. So transfer function models, we have considered last week the dynamic models in the form of ODE. So we will be having the ODE equation. First week, we further solve the ODE equation using the integration method to get the dynamic model. We have introduced an alternative model form based on Laplace transform this week using the transfer function model. Both types of model, either you want to solve using integration method or either you want to solve the transfer function model, you can get the dynamic model. They can also be used to determine the dynamic behavior of a process after changes. Means you apply a change to the system, you can get a dynamic model, solve using the integration method or solve using the transfer function method. A transfer function model characterizes the dynamic relationship of two process variables. So the output we call as the dependent variable. For example, you want to study the temperature change. You want to study the composition change. So this will be the dependent variable. Okay. Independent variable will be the one we call as the input. So independent variable will be disturbance and also the manipulated variables. Okay. Properties of the transfer function, we have the a symbol to represent the transfer function. We use the G. So the G is the transfer function. So if let's say this is the transfer function of the process, then you'll be having GP. So this is the transfer function of a process. If it is a controller, then it will be GC. It means the transfer function of the controller. So G stands for the transfer function. Then the subscript stands for the element. Like for example, it can be a process, it can be a controller, it can be a valve, it can be a pump, it can be the sensors. Okay, so X will be the input, Y will be the output. For example, if let's say last week we learned this, your input is the volumetric flow rate, the inlet. Then the output will be the level of the tank. So this will be your Y, this one will be your X. You'll be having output that you identified from the process. Either it is a level tank, Either it is a temperature, either it is the composition. So depends on the question. The transfer function completely describes the dynamic characteristic of the system. If we select a particular input, for example, this example, it is a inlet volumetric flow rate, for which the transfer function of this one, you will get, like for example, Laplace of function of t will give you the function of x. So if let's say this is the xt, when you Laplace transform this one, you will get the answer of ss. Okay, so the solution using the transfer function will involve Laplace transform. Either it is Laplace transform or it is the inverse Laplace transform. So the equation to represent the output over the input, so you can rearrange. For example, the transfer function is output over the input in the S response. So the output will be the ys. When you rearrange, you will get the equation of product or multiplication between the g multiplied with the ss. So just rearrange to get this output at the left hand side. So it is actually transfer function, you multiply the input to the other side to get the output at the left hand side equals to transfer function multiplied with the x. Okay, by taking the inverse Laplace, meaning that when you perform the inverse Laplace transform, you will get everything back to t. So in capital or small letter, normally the S response will be using capital. So this one we actually will change to the small letter y, because the transient or time response, we are using the small letter, just like the F is a small letter. In the S response, we are using the capital F. Use deviation variables for derivative. Work with the deviation variable. So this one means when we want to use the unsteady state minus the steady state, the difference between these two, for example, during unsteady state, my variable is x. During steady state, my variable, to indicate it is steady state, I put SS, steady state. So this stands for steady state of x. This stands for unsteady state of x. So from here, if we are using a deviation form, so deviation variable, I will be having x prime to indicate the difference using the unsteady state value minus the steady state value introduction. So what is the prime? Prime is deviation. Deviation means I'm using the unsteady state value minus the steady state value. So prime indicate the deviation. Okay, where prime is the deviation variable, so we have the unsteady state value minus the steady state value. So sometimes they do not use the prime. In other textbook or in tutorials, sometimes they use a capital X to indicate deviation. So x minus x, then steady state. We do not write unsteady state over here. So we will just represent using x to indicate it is a unsteady state value. So if you put the subscript SS, it means it is the steady state value. So either you prefer to use x prime or you prefer to use a capital X to indicate deviation variable. Introduction first. So a change is always applied to the system when the system already achieved steady state. So at the beginning, the process must achieve steady state. All the output and input must always same value, meaning that they will not change, already achieve steady state. So a change is being applied to the system at time equals to 0. So before time equals to 0 is no change. At time equals to 0, the change start to apply, you apply a change to the system at time equals to 0. So at time equals to 0, everything equals 0, no change. Because at time equals to 0, even you have applied a change to the system, there the system has no time to respond yet. So at time equals to 0, all the values will be following the steady state value. No time to respond. Just like I adjust the temperature of this room to be 23. Now it's 25. So at time equals to 0, my temperature will be still at 20, the steady state value. I can't remember which value I give just now. Initial value. So no time to change. It will follow the steady state value. It means everything will be 0, no change. Example, work with the change in temperature relative to the starting temperature means it is the steady state value. At time equals to 0, all the values will follow the steady state value because no time to change. So if you want to put an equation to represent this one, you can, for example, I put the parameter of time, parameter of T, temperature. Okay, so this is the T prime. Let's say I'm using T prime to indicate deviation variable of T. So this will be using the unsteady state value of T at time equals to 0 minus the T at the during steady state. Because follow the equation, it will be unsteady state minus steady state. Unsteady state is what is the time. They say if let's say this is a time 0, then this one should follow time 0 at time T. So at the beginning, when T equals to 0, the value will be 0. It is because of at time T equals to 0, this value will be exactly the same like the steady state value. No time to respond yet. Therefore, these two will be the same values. It will give you the answer of 0. Okay, so this one you already learned from, you don't need to memorize this, you just follow the Laplace of the first order derivative. So this one will be follow the term 24. Okay, so this will be the SFS minus F0. So we'll be using this table for this lecture 2 as well. Okay, Laplace of derivative. So from here, when the equation already in deviation equation means we will be using the unsteady state minus the steady state. So this one, if you copy from the solution of term 24, okay, screenshot. So Laplace of derivative will follow the solution of term 24. So when you have first order, you are going to use term 24. If you have n order, then you'll be using term 25. So this term 24, for example, the solution will give you SFS minus F0. So if this is the transfer function, the equation already considered using the unsteady state minus the steady state. So it means F0 will be using this stand for the deviation variable. You are using the value of unsteady state, which means unsteady state at time equals to 0. So let's say because F stands for any variable. It can be T, temperature, it can be composition X. So let's say I put T0, okay? The variable, instead of using a general letter of F, function of T, I use temperature. So this will relate the one previously. This will give you T at time 0 minus the T of steady state. So this whole term will give you 0 because at time equals to 0, this value will be exactly the same just like the steady state value because at the beginning, your temperature has no time to respond. The temperature will be exactly the steady state temperature. So therefore, it explains why you can cancel out this one, which is the F0. Or in this case, I will put Y0. Follow the SYS minus Y0. Follow the term 24. So the initial condition for the equation using the lab transfer function solution, the initial will be always 0. It means your y0 is 0. It is because of this. They already used the unsteady state minus the steady state. At time equals to 0, no time to respond, the value will be exactly the same like the TSS. Or if I put in this way, it will be T0 equals to TSS at time equals to 0. But this is for the derivation variable. Then you have term 25 using this solution. So term 25 using this solution, we have tried in first week of tutorial, power to 3 or power to 4, you can solve this. Okay, so if let's say you solve the model using the transfer function, in summary, as a conclusion, the initial condition will be 0. You will not be using any initial values while solving the model using the transfer function method. It is because of this reason. Initial condition will be 0, and this makes the modeling become simpler. So if you can choose, you are not requested to solve using integration method, then you can choose to solve using transfer function method, because you can ignore the initial condition. For example, temperature, steady state value. What is the initial value of the temperature before the change? So this is the initial value. You don't need the initial value to solve the model if you are using the transfer function method. So it makes the modeling become simpler if we are using the method of transfer function. So in summary, transfer function, we do not need y0. So in this case, to be exact, it will be y prime. It is because of y0 minus yss will be giving you the answer of 0. Okay. Procedure for determine the transfer function for a process, we have the step 1. You have to decide the 3 equations that you are going to use, conservation of law. So for sure, for all the process, you have to start with the mass balance. So if the composition is given, then on top of the mass balance, you have to use the composition balance. If let's say the temperature also given for each strips and it is not constant, then like the one I mentioned, your homework in your week 1, the question actually, it is considered one question. One asks you to derive the model to represent the composition dynamic model. The other part is to derive the equation to represent the temperature dynamic model. So in that case, if the temperature is not constant, then you have to derive using the energy balance as well. So this is step 1. You have to write the appropriate balance equation. And then this example or this week 2 will be harder a bit when the equation, it is non-linear, means it is not power to 1. Then you will be having a long calculation to linearize your variable, your output, to be power of 1. So this will be step 2. If let's say all already power to 1, then you can skip the step 2. But I do include one example where you have the non-linear system. And these normally will be in your final exam, not your test one, because too long already the calculation. So this one you can consider for your FE, final exam. Your test one will be just 10%. Mainly is to perform the health check, whether student attend the class, can still follow the class. So the test will be a simple one if I compare to final exam. Of course, not simple as you think, but if I compare with the final exam, only 10%. So I cannot be having too many questions, bigger scope in test. That's why I keep all these in final exam. But we will practice this in the lecture and also the tutorial. Then we have to define the deviation variable. For example, you have to define temperature prime using the temperature of the unsteady state minus temperature of the steady state. So in short, it is actually US minus SS, unsteady state minus steady state. If let's say the value is constant for steady state or for unsteady state, then there will be no deviation. Like for example, the composition of the inlet is constant, then the inlet composition will be having no deviation because these two will be the same. Only the value of this T during unsteady state and the T during a steady state, they are different, then you will be having the deviation variable. If these two are the same, means during steady state or during unsteady state, the value remain unchanged, then no deviation variable. So step 3 is to define the deviation variable. Step 4, place balance equation in deviation form. For example, you derive the equation using the mass balance dm over dt equals to mass rate in, this one no over dot here. So you'll be having W in minus W out. So this is unsteady state value, unsteady state mass balance. When it is a steady state mass balance, this will be 0. So will be W in minus W out. So these two will be unsteady state mass balance minus steady state mass balance. So if let's say I want to put steady state, to indicate steady state, I will put dm subscript s over dt. So dm minus ms over dt will be the equation of unsteady state minus steady state. So introduction first. So it means your step 4 is actually having the mass balance. If let's say you only have mass balance, then you'll be using the unsteady state mass balance minus the steady state mass balance. If you have energy balance, then you'll be using unsteady state energy balance minus the steady state energy balance to give you the equation in deviation form. Okay, so this is the step 4. After that, you have to Laplace transform both sides. And we have no initial condition for this. So using initial condition, you can skip. Then step 7, you'll be having the, you have to refer to the Laplace transform table, which is this table, to solve, to finally get the model. So step 7. Okay, so we have learned this in the previous week where we say for the first order, the general equation, so this one will be the ODE. We will learn the second order, I think next week or next 2 weeks. I can't remember which week already. So not this week. So this week we'll be still using the first order, majority first order, for you to derive the transfer function. So we have two sides. So we have the t, for example, as a function of time. Example, t as a function of s. So if it is the first order model or process, the equation will be, for example, tau dt over dt plus tt equals to kx as a function of time. I just modified from this equation. This is the time response first order equation. If it is the s response, then you'll be having your ys over your xs, both in capital, equals to k over tau s plus 1. So this is the, we call as the default or standard equation for first order. Either it is in time response or either it is in s response. So from time response to get the s response, it is Laplace transform. If from s response to get back everything in time response, it is the process of inverse Laplace. So that's why you have to learn the basic of Laplace transform in your maths to prepare you for this control module. Okay, so the second order will be this t response, and then this is the s response. The standard equation is not given in the list of equation. You have to memorize the standard equation. We won't be using this. We will be using only the s response. So what you need to memorize here, it is the general equation for first order and the general equation for the second order. So a correction maybe. So this one, don't use the small letter. If it is a time response, let's change everything to capital. Okay, so this is actually your G, transfer function, G. So what is G? G is transfer function using the S response. Okay, so this is the first order transfer function. This is the second order transfer function. Okay, next. So just now we have the first order of transfer function using the standard equation K over tau S plus 1. We have learned the K, the tau, I think the last few slides of week 1. So K is the gain. Gain is the output, total output over the change of input. So this is the gain. For example, just now we're using the tank, the H, and then the input is the inlet flow rate. So in this case, when I change to transfer function, I'll be using HS over the QIS as my GP. So transfer function will be using the capital uppercase, level H uppercase over the input QIS. Okay, so when you apply a change to the QI, it will cause a change to your H. For example, the initial value is QIS. You change to QI. Initial value of this is HS. Then you change to H. This steady state value at the beginning will change to a dynamic model, means the H will change according to time due to the change you have applied to your input QI. So in this case, you have to derive the model, dynamic model. Either you use the integration method or you use the transfer function method. If the question does not require you to solve using integration method, it is easier to solve using the transfer function method. So when you have a change to this QI, so let's say this is my QI. Initial change will be, let's say I increase. So the change will be QI minus QIS. Then due to the change of the QIS to a new value of QI, then you will stand there. If let's say you are having the experimental works to study the change of the level, so you will having this one we call as the ultimate change. Ultimate change. This one will be the initial value. This one will be the final value. So the change of the output we call as the ultimate change of output. In this case, I will use the example of the tank level, which means H. Due to the change of QI from initial value to a new value. So when you have these two values, due to the change of QI, you go there and measure the change of this. So this is the delta Y. So what is delta X? Delta X is QI minus QIS in this example. So if you put this example in, it is clearer. It is actually the output change over the input change. So this is the process gain. If you have a higher process gain, it means a small change of the input will create a big change in output, means you are sensitive. The process is sensitive. I just apply a small change to the input, but somehow due to the higher K value, then the process is sensitive. It means it will give you a very big change in output when you have higher K. So for a linear system, the K will be always constant. It is a constant. But for a non-linear system, the K will depend on the operating condition. So effect of gain K, just like when you have higher K, which means K, it is the ultimate change of output over the input. So this is the output change over the input change. When you have higher K, then you will give you gain K describe the magnitude of the change. Means it change more when you apply a change to the input. Then when K is higher, you'll be getting the slope is higher. Delta Y over the X. So this is Y, this is the X. So what is gain? Gain is the ultimate change of the output over the input change. Using this example, tank, simple example tank, my output change is the H. You are going to plot the graph from the initial condition to achieve the steady state. So a change applied to this QI. You stand there. For example, you go to adjust the flow rate. Okay, then you don't touch anything. Observe the change of the tank level. You plot the graph until the system achieves steady state. Then from the graph, you get the value of the total change of the tank level over the change you have applied to the flow rate. So this will give you the process. When you have higher K, means the process will be faster. When you apply a change, it will actually having a high change in delta Y. Okay. Time constant. So where do you have this time constant? G over the K over the tau S plus 1. So tau. Time constant means the definition follow the first order without the time delay. Time constant means it is the time taken for the process to achieve 63.2% of the total change of Y. So let's say you have a high tau. It means the process is very slow because you need more time to achieve 63.2% of the total change of output. So what is total change? Well, let's say tau equals to 1. This will be your total change. So let's say the change of the Y is from 0 to 1. Okay, how you solve the tau using graphical method. How to solve tau using graphical method. So let's say tau equals to 1. The total change delta Y, it is 1 minus 0. 1 minus 0. So the change is 1. 63.2% of the change means you divide by 100, multiply the total change of Y. In this case, it is 1. So it is 0 means you divide by 100, then you multiply with 1. So it will be 0.632. So 0.632 about here. So you go here. This point, let's say tau equals to 1. How you get tau equals to 1? You go down. You will get the answer tau equals to 1. Example. So what is tau? When you have bigger tau, means you will need more time to achieve steady state. If you have smaller tau, means the process is super fast. So conclusion, when you have bigger tau, means sluggish process. Sluggish process means it will take longer time to achieve steady state. So follow this curve, the steady state is here. And this one still not, I cannot conclude this is a steady state, because steady state, at least you must be having 3 value continuously, same value. Okay, so you can see when tau equals to 4, it does not achieve steady state yet. It means that when you increase your tau, it will take longer time to achieve steady state, which it is not desirable, means not desired. You always aim for smaller tau. Smaller tau means the process is faster. Faster to achieve steady state, which means you will achieve this steady state when you have smaller tau. When you have bigger tau, the process will be sluggish. It means based on this observation, it does not achieve the steady state yet. So what do you want? You want a small tau instead of bigger tau. Bigger tau means the process is very slow, sluggish. sluggish. So bigger tau, you don't want. So if you want to compare, you want to design a process, we always want a smaller tau instead of bigger tau, because smaller tau will have a faster process to achieve steady state, and bigger tau will take longer time. Like this example, we still haven't actually got our steady state over here. So larger tau means a slower process, means sluggish. So it is an index to indicate how fast the process is. If you are given tau 1, tau 2, tau 3, like tau 1 is 1, tau 2 is 2, tau 3 is 4. So the question can be a simple question, which process is faster? It means tau equals to 1. So this is where we use the tau to check whether the process is stable or not. Okay. Develop a transfer function for the first order. Now we are going to start to derive the equation for the first order. So we have the example 1, which is the mercury thermometer process. So I need you to actually solve this one together with me. So I will actually having this example, mercury. So we will having few examples. So we cover this example first. Okay. So this is the example 1, mercury thermometer process. So step 1, you have to write the balance equation. So this is the mercury. The temperature inside, you want to check the temperature of the mercury, it is your output. So it is the Y. So why you use the small letter? Because this is a time response. S response has no meaning. Whatever you get in S response, you have to inverse Laplace to get back T response. Only then you can substitute the time value to get the answer of this Y. So the temperature of the reading is YT. It is in the time response. The temperature of the surrounding, it is the XT. So this is the outside temperature, or this is the surrounding temperature. Okay, so input minus the output equals to the rate of accumulation. You have learned this. We have to use the energy balance. dE over the dt equals to the rate of energy going in minus the rate of energy going out. So in this case, we assume the wall of the thermometer is super thin. Then you can ignore conduction. So the heat from here to flow inside the thermometer, the mercury, will only involve the heat transfer function mode of convection. So this is the in, which means the temperature of the X at time equals to 0. It is higher than the temperature of thermometer reading at time equals to, I put T equals to 0. So your XT is larger than YT at T equals to 0, time equals to 0. Therefore, the heat flow in this direction due to this statement assumption. The surrounding temperature at the beginning is higher than the temperature of the thermometer. Therefore, you have the heat transfer from the outside air into the mercury inside the thermometer. And we assume there is no energy transfer out from the thermometer mercury to another side of temperature of the surrounding air. So no. So you do not have any E dot out. No heat loss from the mercury to the surrounding air. So you only consider in. So therefore, this one will give you 0 due to the heat transfer stop when you have the heat only transfer into here, and there is no heat transfer from this point to here. No. Therefore, you do not have the E out. Cancel. You do not have the E out. So you only have the E dot in here. And we have the assumption thin wall. So therefore, you only need to consider convection, where convection equation Q dot, or I put as the E dot in, it is using the equation of HA delta T. So this delta T is the gradient temperature difference between the X and between the Y. Because at the beginning, you assume the surrounding temperature is higher, so it's X minus the Y. So YX minus Y, or you can put here at the beginning, surrounding is having higher temperature. Okay, and this one because the E dot out is 0. And your dE over dt always use one simple equation, M, mass of the mercury, multiplied with the heat capacity of the mercury, multiplied with the change of temperature inside the mercury, which means you are using D. If let's say sometimes they change the Y into temperature, then you have to change this to T, dt over dt. In this example, it's Y, so it is dy over dt, dy over dt. So this is last time the equation of mc delta T over dt, because you are using the rate of heat, means power. You have to divide by time. Okay, so you'll be using the equations of mc dy dt. So I'll be solving this one with you all using a clean one. So this one. So you can sketch a bit like this. This is X, this is Y. Okay, so you have the heat transfer from here, but you do not have the heat transfer for this one. And you only considered the convection. Therefore, you'll be using the equation of dE over dt equals to E dot in minus E dot out. An equation for rate of energy is using a simple equation mCp d. Temperature is Y in this example over the dt. So this one is actually mc d temperature over the dt time. So now your temperature is equivalent to the symbol of Y in this example. Hence, I'm using the dy over dt. Okay, equals to convection. So you do not have this E dot out. So E dot out don't have, equals to 0. And your E dot in only involve the convection. So convection is using HA delta T. It means you're having higher temperature X minus the lower temperature Y. So HA X minus Y. So this will be the equation. Then this one will be the 0 here. So don't need to write. So this is the equation we call as the unsteady state energy balance. So if it is a steady state energy balance, we will actually include the subscript of S or SS. So in this case, I use the S subscript of S to indicate steady state. To indicate steady state. So mCp dys subscript HA XS. So this one is a small letter because it is the S response. Small letter XS minus YS. So S stands for the steady state. Because you are solving this example using the transfer function method, so you have the equation 1, equation 2. So you are getting the deviation equation. Deviation equation. So 1 minus the 2. mCp d and then y minus small y. Minus ys equivalent to HA, then X minus XS, okay, minus Y minus YS. So this is equation 1 minus equation 2. So when you expand this equation, then you will get HA x minus XS, okay, minus HA y minus YS, equivalent to same thing, copy dy minus ys, and don't forget the dt. Previously we have dt. So this is the derivation equation. Okay, then you have to introduce derivation variable, which means you have to introduce derivation variable where you have, okay, introduce the step, introduce derivation variable. For example, I'm using capital Y to represent unsteady state minus steady state. Capital X, unsteady state minus steady state. Done already. So this equation will be simplified using the derivation variable. So MCP d big Y over dt, HA big X minus HA big Y, because I introduce the derivation variable. So steps are the same for all the examples. First, consider the balance you want to use. In this example, we have the energy balance. And then we'll be deriving the unsteady state energy balance and steady state energy balance. Then we use the equation 1, unsteady state minus the steady state. So the steady state, we will just include the subscript of S to indicate it is a steady state. So once you have the equation 1 minus equation 2, where this is actually the unsteady state minus steady state, then you will introduce the derivation variable, where you have the capital Y and the capital X. Or you prefer to use Y prime, X prime, up to you. Both also accepted. Okay, they are acceptable. You can use either, but you have to introduce, you have to let me know either you use Y or either you use the prime. You have to indicate, you have to introduce the derivation variable. So once you have this already, then you proceed to Laplace transform both sides. Okay, you have to Laplace transform the both sides. So in this case, I won't be arranging, I won't be finding the tau at the beginning, but I will know what is my tau at the end. So I do not follow the steps. Like for example, in this slide, assume the tau to be this at the beginning. I do not assume anything. I will keep deriving until the end. And then I will change the equation to follow the standard equation of first order. Then I will know what is my tau. I will know my tau will be MC over HA, rather than I memorize at the beginning what is the tau equals to MC over HA. I don't want to perform this step because I don't want to memorize the tau equation. So you can proceed like this. Then what you need to do is Laplace transform both sides. So you will put Laplace transform both sides. So in this case, you'll be getting the coefficient you don't touch. So you'll be having MCV SYS minus Y0. And you are using unsteady state minus, or this one to be exact should be follow the derivation. So this one should be Y0. And Y0 means it is Y at time equals to 0 minus Y during steady state. At t equals to 0 time, these two values will be the same. So that's why one of the slides they say transfer function solution is easier because initial condition will make these two same. It is because of at time equals to 0, the temperature of the thermometer will follow the steady state value. No time to change yet. Just like you are having initial temperature of the thermometer at 24. So at time equals to 0, the thermometer reading still 24. No time to change because it is just the beginning of the change. Therefore, these two values will be the same, will give you the y0 equals to 0. You can cancel the initial condition, don't need. So MCP SYS minus y0, then continue the other side. I will move this one down a bit to this. So let me make it nicer. Okay, so this one will be 0. Okay, HA. So when you Laplace the x, it will be XS. When you Laplace the y, it will be YS. Okay, just like you Laplace the F, you will get FS, capital. When you Laplace the x here, you will just need to change these to response of S. So it will be XS, something like this. Okay, so from here, next, you have to rearrange the equation to have the output at the left-hand side, and the rest of it will be moved to the right-hand side. So MCP, your output is YS, so I will be moving my output to the other side, left-hand side, HA YS equals to HA XS. And then factorize the common term YS. So you'll be having MCPS plus HA bracket, this one bracket, equals to HA SS. Then you need to have output over the input, means YS over the XS will be finally HA over MCPS plus HA. And you have to change the equation to make this equation to look like this general equation, tau s plus 1. So this is the last step where you have to change the last term into 1. Then you divide the whole equation with HA to give the final equation of 1 over MCP over HA S plus 1 to be K over tau S plus 1. So your K is 1 and your tau is finally this. So this will be your K, this will be your tau. So this is the standard steps. We derive the first order. Use the unsteady state balance minus the steady state balance. Introduce the deviation variable. Laplace transform both sides. Rearrange the equation to get the output over the input. And then compare with the standard equation of the first order, K over tau S plus 1. And finally, you will solve what is the K and what is the tau, based on the comparison of using the standard equation of the first order transfer function. So this is the first example. Then we will continue with the second example after the short break. 5 minutes. So 5 minutes. So we will take the attendance. Then we will come back for the second example. So this, you have to use the composition balance. Okay, so we will take the attendance first. Then we break for 5 minutes. Okay. Okay. So now is example 2, mixing process. Mass of sugar. So this is sugar. Sugar. This one wrong. Correction. Sugar. Okay. Concentration. Okay. So example 2 is mixing process. We have a mixing process which a stream of solution containing dissolved sugar flow as a constant volumetric flow rate of Q. So this Q is constant into a tank, constant hold up, V is constant. You have derived previously dm over dt equals to mass rate in minus mass rate out. So when you have the volume constant, rho equals to m per v, then you'll be having m equals to rho v. So now v is constant due to the description of this constant hold up of v. Then you'll be having d rho v over dt equals to 0. It is because of the volume is constant. Then we're having mass rate in minus mass rate out. So in this case, what is the mass rate here? The mass rate is the equation you can use mass rate using the relate to the concentration. So relate to the volumetric flow rate. Let's say you have rho given, Q given. So this is the density multiplied with the volumetric flow rate. So you can check with the units. For example, I'm using m per volume. I'm using meter cube multiplied with volumetric flow rate over the time. So I will get my mass. So I'm using, I'm using volume, general equation, volume, general symbol. I'm using volume. So this one is rho and Q. So I will get final will be mass over the time. So I'm using the rho multiplied with the Q to get the mass rate equation. But this is about concentration. So if the volumetric flow rate is given, then density is given, then you can use the mass rate using the equation of density multiplied with the volumetric flow rate. But this example, density is not mentioned or stated, not stated in this example. So your mass rate, you should relate to concentration, C, multiplied with the volumetric flow rate, Q. Because this parameter given is the concentration instead of density. So if density is given, concentration is not given, then your mass rate should be utilizing rho multiplied with the Q. So if concentration is given like this example, concentration is given, concentration is actually the mass over the volume multiplied with the volume over the time. So when you cancel, you will get the mass over the time, which means this is the mass rate. So you'll be using CQ, C concentration multiplied with the volumetric flow rate, which is Q and Q. So in this case, dm over dt equals to W in minus W out will be your mass balance. Then your W. So this sometimes we use the mass rate, sometimes we use the W. They are the same. Either you use the mass dot over dot or W. Both of them indicate mass rate. Okay, so either you use the mass dot in minus mass dot out. They are the same. Okay, so because volume is constant, then this is one of the parameters given to you. This one, I keep it here, but you are not using this in this equation, using the rho V, no, because the parameter given in this question is concentration, not density. So you don't every equation of mass balance, you go to multiply rho, multiply with volumetric flow rate, no. For this example, you have to use the concentration multiply with the volumetric flow rate. You can play around with the equation and then you can derive the mass rate. So concentration multiplied with the volumetric flow rate will give you mass rate. So this is the conclusion. So this is the mass rate. Okay, now we have the inlet volumetric flow rate Q, same with the exit volumetric flow rate. And the concentration of the sugar in the entering stream is given as X. So this X is concentration. It is not in percentage, it is in the equation, for example, concentration. So it will be mass over the volume, give you the concentration. They do not give me the unit, so I just relate the formula. Concentration is mass of the solid inside the liquid mixture with the volume of V, for example, mass over the volume. And the Y stand for the exit concentration. Okay, exit concentration. So you have the entering concentration and the exit concentration. Entering concentration is X, exit concentration is Y. It is desired to determine the transfer function relating the concentration of Y. So your accumulation term is the exit composition. Oh, sorry, concentration. Exit concentration. So you'll be using the mass balance for this simple example. So I'll be using this, sketch a bit. So here, entering is X, exit is Y, volumetric flow rate is Q, volumetric flow rate also Q here. Okay, so you start with the dm over dt equals to mass rate in minus mass rate out, or you prefer to use W in minus W out. So this stands for the mass rate. Okay. You will be deriving just now the step to relate what formula you are going to use for the mass rate. For example, in this example, we are using the concentration multiplied with the volumetric flow rate. So I put here, mass rate, you have to use concentration multiplied with the volumetric flow rate. For this example, volumetric flow rate. So if this is M, then it will be concentration multiplied with the volume. Okay, so this will give you concentration. So we'll be having the M here, concentration multiplied with the volume, and this is constant. Pull up means V is constant. So we will expand this equation, mass rate in minus mass rate out, using M equals to concentration means Y. Okay, then volume is using the V. So I'll be having D, M stand for Y multiplied. So V is constant, so V is outside, dy over dt. Because of accumulation term. So you expand the M equals to Y multiplied with the volume. So D, then you have the dy. V, volume is constant, so you factorize the volume outside. Then mass rate is Y multiplied with the Q, X multiplied with the Q, because we are using the concentration multiplied with the volumetric flow rate. So for entering, X is your concentration. This one is your volumetric flow rate. So in. they are using the in. Let's say this is a Q in. Then Y is your concentration. This one is your Q out. So you are using the formula of in minus the out. So you'll be having C already changed to the formula of X, symbol of X, multiplied with the Q in. So this is the in minus the out. So will be YQ. So it's actually using concentration multiplied with the volumetric flow rate. So this stands for the in, this stands for the out. So you have derived the mass balance. So this is unsteady state mass balance. So now using the unsteady state balance change into steady state mass balance, we'll be using subscript of S, B dys over dt equals to xqs minus yqs. Sorry, the parameter is x and y. So you'll be using xsq minus ysq. So we will put always the coefficient at the front. So this equation we will change to qxs minus qys. So v dys over dt. So this is the unsteady state and steady state mass balance. So this is unsteady state. This is steady state. So we'll be using this equation for our steady state mass balance. Then repeat the same. You are using equation 1 minus equation 2. So equation 1 is V, then D, then bracket Y minus Ys over dt equals to Q outside, then X minus SS minus Q Y minus Ys. So this is unsteady state mass balance minus steady state mass balance, equation 1 minus equation 2. Okay, so once you have derived the equation in the deviation equation, you have to continue to introduce the deviation variable. So it repeats exactly the same like the previous question. Let's say I'm using capital. So y equals to y minus ys, x equals to x minus xs, and sub this one into this equation to simplify the equation to become deviation variable. So I'll be having where's my equation? V d okay, v dy over dt equals to q x minus q y. Then repeat the same Laplace transform both sides. You'll be having vs ys minus y0 bracket equals to qxs minus qys. Initial condition will be 0 for the deviation equation. Follow the same concept just now. So you rearrange to have your output at the left-hand side and your input at the right-hand side. Factorize your output. And then qxs, rearrange the output over the input. You'll be having q over vs plus q. And you compare with the first order of transfer function, you will be divide the whole thing by q. So you'll be having 1 over V over the QS plus 1, where this is your K, this is your tau. So K is 1, tau is V over the Q. So we have derived the second example, which is the mixing process involving the concentration and the volumetric flow rate. We have example 3. And then the last example, which is the log 1 nonlinear. Okay, so we will go to example 3. You get the concept? I will share this written copy in Telegram. So if you couldn't copy now, too many things, maybe you put a note there. What else you need to know for this is actually compare with standard equation, where standard equation is K over tau S plus 1. Don't follow the solution in the slides where they actually assume the tau from the beginning. We don't do that. We will get our tau at the end of the answer by comparing it with the standard equation. Okay, so next. The third example is the level process, where they give you the density and the volumetric flow rate. So you can put your mass dot, which is the mass rate, or you prefer to use W. You can relate the equation to rho Q. So if let's say this is the mass, then you'll be using rho volume. Okay, you'll be using this. So we'll be solving this. So I put it here. This is a simple example of inlet volumetric flow rate QI. Volume for this example, I think they actually have rho A. Okay, you are going to derive the level, so the change of the level. Then you have one valve here. When you have a valve there, you have to consider the resistance to flow. Resistance to flow means this is your exit flow rate. So this is the exit volumetric flow rate. Resistance to flow means this Q is affected by the head, which is the tank level. If the relationship is not given, it will be a linear equation to relate Q and H. So Q equals to H over the R. It means when the level in the tank is higher, the Q will be faster. If the equation is not given, we will be using the linear equation. The higher the tank level, the faster the flow rate, exit flow rate. So the equation will be using Q equals to H over the resistance of the valve. The resistance of the valve will be given. So in this case, we do not have mass balance, so we can ignore the composition balance. We do not have the temperature given for the stream, so there is no energy balance. Then we only have mass balance. Okay, mass balance. So in this case, dm over dt equals to W in minus W out, or you prefer to use mass rate in minus mass rate out. So rho equals to m per v, m equals to rho v. So this equation will be d rho v over dt equals to mass rate. So mass rate will be using rho q, which means you use the density multiplied with the volumetric flow rate. So it will be density in inlet flow rate or volumetric flow rate minus density exit flow rate, exit volumetric flow rate. the density will be constant if, let's say, because it is the same fluid. So in and out will be having same density. So density will be cancelled out later on. So you expand the volume. Okay. Oops. So volume, it is cross-sectional area multiplied with the tank level. So in this case, density is constant, therefore you factorize outside. Then D, A also constant, so A will be outside also. Then left with dH over dt. Okay, so density move here, expand the V equals to AH. A also outside because A is constant. Rho and V, sorry, rho and A. I want to write A. Why put the V there? Rho and A constant. So you'll be moving the density and area outside, then equivalent to rho Qi minus rho Q. Okay, so you can cancel the density. You'll be having A dH over dt equivalent to Qi minus Q for your unsteady state mass balance. Not enough space. So this is the unsteady state mass balance. Then derive the steady state mass balance. You'll be having equation 1, equation 2. So just add the subscript here. dHs over dt equals to Qis minus Qs. Then you use the equation 1 minus the equation 2. Repeat. Introduce the deviation variables and then Laplace transform both sides. Rearrange to get the output over the input and then compare with the standard equation of the first order. You will finally find what is your K and what is your tau. Okay, so one more page. So you will introduce deviation variable. So let's say I use a capital H to indicate H minus HS. Then capital Qi, sorry, this is constant. So the one change is, yes, the one change is Qi. So Qi is Qis unsteady state minus steady state. So Qis. Okay, so you'll be having just now the equation 1 minus equation 2 simplified to A. So just now equation 1 minus equation 2 is A d H minus HS over dt equals to Qi minus Qis minus Hi, there's no I there, H minus HS. So this is my equation 1 minus equation 2. So I should move this one actually after, or I already derived that one. I haven't. So I should move this. So I should move this one after that. Okay, you should use the unsteady state balance minus the steady state balance first, and then only you introduce the deviation variables. Okay, so this equation will left with A dH over dt equals to Qi minus H. Okay, repeat the same. Laplace transform both sides. You'll be having ASHS minus H0 bracket Qi function of S HS. Initial condition will be 0. Okay, it is because of the value will be the same like the steady state value at time equals to 0. So you rearrange so that you can group the output at the left-hand side and the input at the 2IS. So you'll be factorize the HS. So AS plus 1 equals to QIS. Okay, just now here, correct. Then you'll be having output over the input equivalent to 1 over AS plus 1. This already in the form of K over tau S plus 1, where your K is 1 and your tau is. Where's the R gone just now? Yes. Your H over the R. So minus. Okay. Go back to the previous. We have to substitute this one equivalent to H over the R. So I do not erase anything, just a correction. So this one will be H over the R. It is because of we have derived the Q equals to H over the R. Okay. So then I go to the next page. Okay. Then this one also cancel H S over the R. Okay. Correct. Here, able to copy because we need to substitute the exit flow rate using the formula H over the R. Okay. So therefore, here is additional over the R. Then the rest will be just over the R. AS H over the R. Over the R. Over the R. Okay. Then you will be using your maths. How to solve this? Yeah. Then this one will be like A R S plus 1 over the R. Correct? So I will just erase first. A mistake. So HS ARS plus 1 over the R equivalent to QIS. Okay, so you're having HS over the QIS equivalent to reverse R over ARS plus 1, where it is K over tau S plus 1. Okay. So this one is the example 3. So example 3, they have level process. Okay. So you can repeat the same one for different condition, which is this slide. Okay, I think this one I will share with you. Don't worry, it's just the same steps. A little bit mistake over there. So what if it is a constant flow outlet, which means you have the same Q. Q is constant. So just now the condition, let me check again the condition. What is constant? Level 3. Okay. So final answer ADH. Or what I derive? Oh. So R over tau S plus 1, which means you have the AR S plus 1 over the R. Correct, my answer? Let me check again. Yes, R over ARS plus 1, correct. So R over ARS plus 1, R ARS plus 1, correct. So same example, different condition. What if your Q is constant? Then you will repeat everything the same using the concept just now. Mass balance, so dm over dt equals to in rho qi minus rho q. Okay. So you'll be having this value, you have to put a subscript qs. It is because of in the question they say q is constant for your equation 1. So equation 1 will be rho a dh over dt. Then repeat the same, rho a dhs over dt equivalent to rho qis minus rho qs, equation 2. So when these two during steady state constant, which means when you use the equation 1 minus equation 2, you won't be having this q in your equation. So you'll be having density, cancel first. So equation 1 minus equation 2 will be A dH minus HS over dt equivalent to QI minus QIS. Then this one cancel because Q is constant. So you'll be having this equation. Introduce the deviation variable. You will change A dH over dt equals to QI. When you Laplace transform both sides, you will get AS HS minus H0 equals to QIS. So initial condition will be 0 for this one. Hence, you'll be having AS HS equals to QIS. So when you rearrange output over the input, you'll be having 1 over AS as your final answer. This is when you have Q, which is the exit volumetric flow rate, is constant. When it is constant, during the unsteady state mass balance, you should put your Q as Q subscript S. Okay. So from here, you will have final transfer function, which is a simpler form when there's more constant. Like for example, in this example, Q is constant. So you will get finally the answer is this one. You see in the textbook, they won't derive for you again because they are the same steps. So you just perform this again. And only one thing you have to take note, it is this one. So when you use the equation 1 minus the equation 2, this one gone because of 1 minus 2. Gone. Same value. Just like you have 5 minus 5 equals 0. Same value. So from here, final answer will be this. When you repeat the same steps, Laplace transform both sides, rearrange, get the output over the input. So the last example of today will be the hardest one because longer. Okay, this is things to read, but I will derive the simple one for you, like this one. dE over dt equals to, the last one is the non-linear, is the hardest. I can say the star question. Not this one just the simple one. This is the energy balance. So you can put some notes over there. This is using the equation of E dot minus E out. So to expand the equation of the energy is using the exit. So the equation is mCp, temperature. This is your output. So your accumulation term should be dt over dt. Because you want to study the change of temperature versus the time. So this will be your output. This question, you want to study the change. So the question is to derive. For example, this is the input. So it will be transfer function equals to temperature over the Ti, inlet temperature. So let's say this is the input. So dt, so is omega Cp Ti minus T reference. Then out is this one, so minus. Again, mass rate is the same, omega Cp T minus T ref. So assume T ref equals to 0. So this is the equation 1, which is the unsteady state equation. Then include the subscript S to indicate steady state. So you'll be having TIS. So let's say this is 0, it will be gone. Then minus omega Cp Ts, equation 2. So we repeat the same and continue until the end. You will be deriving the equation finally to be this equation. Heating process, this equation. So try to derive this. So I will put some important steps there. So let's say you have this one already. So I will just copy the whole thing. Okay, so have one more page. So this is energy balance. Okay, if I got time, why not? I derive until the end. So you have the equation 1 minus the equation 2, and remember to expand the m equals to rho v. I think they derive rho v, correct? Rho v. So I'll be having equation 1 minus equation 2. So rho v, because I expand the m, so Cp dt minus Ts dt equals to factorize, okay, never mind, WCP Ti minus Tis minus WCP T minus Ts. Then you use the T prime to indicate the deviation variable. So introduce deviation variables. Then you'll be having Ti prime. You cannot use the capital to indicate the deviation form for this example. It is because of this one already in its uppercase. So you'll be using the prime to indicate the difference between the unsteady state minus the steady state. So I'm using the prime here, Ti minus Tis. So you will simplify this equation to be rho v Cp dt prime over dt equals to omega Cp Ti prime. Then you can factorize the WCP outside minus T prime when you use equation 1 minus equation 2. Okay, so once you have this, then you Laplace transform both sides. So the steps are the same. You'll be having rho v Cp as the coefficient. So you'll be having St prime S minus T prime 0 bracket equals to omega Cp Ti prime S minus T prime S. Okay, initial condition will be 0 and move all the output to one side plus omega Cp T prime S equivalent to input omega CP means I expand this and move this one to left hand side. So WCP TI prime S. Then factorize my T prime S. I'll be getting rho V CPS plus omega CP equivalent to omega CP TI prime S. So rearrange output over the input. It is very simple, follow the same step. You just have to be careful. So omega CP over rho V CPS plus omega CP. Compare with its standard equation K over tau S plus 1. Therefore, you have to divide the equation by omega CP, omega CP, omega CP, and finally the answer will be 1 over rho V per omega. CP is cancelled, so I don't erase anything. You can cancel later. S, this one plus 1. So your K equals to 1. Your tau equals to rho V per W. 1 over. The same answer. 1 over omega C. Maybe some mistake over here. I can't check now. But the steps, you check the arrows later. You will be getting the final answer as this one. Oh, this is the Q. Okay, different scenario. Different scenario. I forgot about this Q just now. So this is one of the additional example. The one we derive in the class is, I assume Q is constant and Ti is not constant. Okay. The solution of this you will get is when you assume, you see the answer is different because we assume different thing. We assume Ti is constant, Q is not constant. So in this example, you'll be having unsteady state energy balance equals to m Cp dt over dt equivalent to in omega Cp Ti S because Ti is constant. Then you have to put the subscript of S here. Hence, you can see finally Ti is gone. It is because Ti is constant. Ti is gone because Ti is constant. Therefore, you have to put TIS in the unsteady state energy balance. So you have, if you refer to the tank here, you have two energy going in. One is here, one is here. So you have to plus Q, okay? And then minus omega Cp, then the T. Then you repeat the same. You'll be having omega Cp TIS minus QS, plus QS minus omega Cp TS equivalent to mCp dTs over dt, equation 2. And expand the m equals to rho volume. Then you will be able to derive the equation of output over the input as this equation. So treat this one as additional example where we assume different thing. So please take note. We assume different thing, you'll be getting different answer. First example I derive, I assume Q is constant. Ti is not constant. Therefore, my answer will be having Ti here. TI is here. Second example, which derived from the textbook, assumption should be mentioned in the question. They should say Q is not constant, but TI is constant. Hence, finally, your answer, you'll be getting the output over the input. The input is the one not constant. The one constant will be gone. Okay, so we have another 9 minutes. So linearization. So let me go through very fast. I will demonstrate the solution, full solution for this one during our tutorial. But what you can prepare first is this one intro, don't need. Okay. So example, you have this exit flow rate. Previously, the example is Q naught output. If the relationship between the H and Q naught not mentioned, we will be using the standard equation to relate them, which is the linear equation Q naught equals to H over the R. In this question, Q naught, it is not H over the R, but they give you Q naught equals to CH power to 1 over the 2. So if you derive the mass balance, dm over dt equals to mass rate in minus mass rate out. So expand the m, the same thing, it is rho v, rho ah. So this will be rho a dh over dt equivalent to the mass rate, rho q, inlet is q, exit is rho q naught, and you sub this as c h 1 over the 2. Then you check your variable h. H is your output. Okay. It must be power to 1. So in this case, the equation of H, which is this in particular, it is not power to 1. It is power to 1 over 2. So hence, you have additional step we call as a linearization step, long calculation, to make this H power to 1 over 2 into H power to 1. So you need to do some revision of the Taylor series expansion. The equation is not given. Okay, so the Taylor series expansion, the equation is given in the tutorial, I think so. Okay, so let me copy the equation of the linearization. So we will be solving this example. If you only one student have class, right? How many students have class? Now at 4? I think 2 students. Let me finish. Okay, I will record a session. If you need to leave, you may leave now. I will record a session and share with you. So let me finish this linearization. So this is the tank we have. The one going in is Q. The one exit due to the valve, you'll be having a resistance to flow. So this Q naught is given the equation of CH power to 1 over the 2. So just now we have the parameter you want to study, the output is H. So in this case, we have derived the equation of mass balance. So before we start everything, just now we have derived the mass balance. Then we already checked the parameter H is not power to 1. Then we have to use the Taylor series expansion. Taylor series expansion. So the equation is Fx. Start at x equals to a. Don't need to memorize, this equation will be given. It is a summation from n equals to 0 until infinity. Then this is a derivative n order. If you start from n equals to 0 until n equals to 5, then it will be derivative of power of 5 from n equals to 0, plus them all together, example. But for this case, we will stop at linear, means we will stop at 1, because we want to get h power to 1, right? So this one later on we should stop at n equals to 1, because we want to get linear form of h power to 1. So your n equals to 1. Okay, so factorial and then x minus a power to n. Okay, so now you have your q naught. So previously we stopped at the equation. Okay, we derive again. So mass dot in minus mass dot out. We have rho a dh over dt equivalent to rho q minus rho q naught. Okay, density can be cancelled. So q minus, your q naught is ch power to 1 over the 2. So highlight this. You have to perform additional step, which is the linearization step. Which means this equation, parameter f now will be changed to, what is your parameter? This whole thing is what? Q naught. So this is your Q naught. The variable inside is h. So how we change the general equation of Taylor's equation to fit the Q naught. Now your parameter is Q naught. Your Q naught is ch power to 1 over 2. So function of x means it is Q naught as your parameter, and this Q naught involving h parameter. So the x here is your h. Because you change, like for example, this is x. Now your x variable becomes h variable. So this is x, you have to change h. Then what is the a? A is where you start your change. It is steady state value. So h equal hs. Then start from n equal to 0, stop at 1. F now become your Q naught. So your Fn will be your Q naught. I will put n. Then your A is here, your Hs. Then n factorial, then multiply. So I will move this equation on a bit. So you have to change accordingly. So x, by comparison, your x is here. Your x is h, variable h. Then your a is where you start, hs. Okay, so you are going to solve the Taylor series expansion using this equation. So in your test and final exam, general equation will be given, which is this one. You have to change into this equation. This equation will not be given. This, yes. So you have to change into this equation. So now your job is how to solve this. Okay, so recap. This is derivative. Then the h inside you sub with the answer of hs. This is the n factorial, and this is the h minus hs power to n, and this is the summation. So this equation, if you expand, you have to check, you have to include n from 0 to 1. So this equation will be expand to Q naught, start from the 0, hs over 0 factorial, h minus hs power to 0. So here is power. This n is power. This n you have to do derivative. Okay. So what is q dot 0 derivative? So this is 0 derivative. Zero derivative means q not exactly the one like ch 1 power to 2. So this means max 0 derivative. You will follow exactly the one given to you. Then of course, when you have q dot power to, it's not power, 0 order derivative, hs, then this one will be chs 1 over the 2, which you already solved this part. I will put it here. The answer is chs power to 1 over the 2. So this one is power. Okay, then we continue because it's a summation. Summation. You already done the 0. You start from 0 until the n equals to 1, so plus. So q naught, first order derivative. So this is first order derivative over 1 factorial. Then the h later you substitute with hs. H minus hs power to 1. It's a simple math. So you already solved this, where I put a tick there. So h minus hs power to n power to 0 will give you the answer of, anything power to 0 will give you the answer of 1. Anything power to 0 will give you the answer of 1. So this one is power. So this one will remain as hs. So h minus hs solved. So how about first order derivative? So it is the same like this. You have your q naught given as ch 1 over the 2. So first order derivative will be 1 over the 2 ch negative 1 over the 2. This is your maximum. Then this whole thing here, q naught s sub the h equals to hs. You will have 1 over the 2 chs negative 1 over the 2. So therefore, this whole equation will become ch 1 over 2. So this one is the s over 0 factorial will give the answer of 1 as well. So this one is 1 plus this whole thing, 1 over the 2 chs negative 1 over the 2. So this one move down, h minus hs. So this is Taylor series expansion. Why we need to apply here is to change this h power 1 over 2 to h power the 1. Therefore, you have to utilize Taylor series expansion. So when you have this already, then you continue. Okay, the one you need to leave early, you may leave. You can refer to the recording later. Okay, then you will sub into the equation. So just now, as a summary, you were having q naught, summary conclusion of q naught initially ch 1 over the 2. Finally, based on this simple Taylor series expansion, you will copy. So this whole thing is actually your q naught. Okay, your q naught initially is ch 1 over the 2. Now become this. So your q naught is, this is the initial. After the linearization, now your q naught become chs 1 over the 2 plus 1 over the 2 chs negative 1 over the 2 h minus hs. Okay. Then just now you have your unsteady state mass balance, which you have derived AdH over dt equals to Q minus Q naught. Just now, this is the U unsteady state mass balance. And your steady state mass balance should be dHs over dt equivalent to Qs minus Qos. So you'll be having this Q naught, initially CH 1 over the 2. You will substitute this whole thing with this. Because this is your Q naught, initial. After linearization, it becomes this. So you will substitute this one to replace this one. Which means your equation 1, this is your equation 1, equation 2. Your equation 1 will become A dH over dt equals to Q minus, you substitute the whole thing inside. So this one, before you substitute, by maths, QO is CH1 over the 2. So if let's say it's CHS1 over the 2, your H value is steady state value, then this one will be equivalent to your Q naught S. So go back here. So we will substitute this with Q naught S because of this. So Q naught S, okay, this one, not this one, the next one. So this one is, these go down, so this whole thing will be minus, I put outside. So substitute this one to here, Q naught S plus 1 over the 2, CHS negative 1 over the 2, H minus HS. So this will be my new equation 1. My equation 2 will be dHs per dt equivalent to Qs minus Qos. This is my equation 2. So now you use the equation 1 minus equation 2. You'll be having A dH minus HS over dt equals to Q minus Qs. This minus remain outside, minus. Then I will be having like this, QoS minus QoS. So it will be gone later, okay? Then you minus the rest. You'll be having plus over here because here have nothing already, so this one will be everything here. 1 over the 2 CHS negative 1 over the 2 H minus HS. Okay, so this one will be gone. It is not hard, it is just long, lengthy. You try 2 times, then you will feel better and more confident. We'll try one more time when the time tutorial. So when you have this will simplify the whole thing to be A d H minus HS equal to Q minus Qs, and because this is gone, then minus 1 over the 2 CHS negative 1 over the 2 H minus HS. This is the US minus SS. So this is the one we call additional step. There must be some preliminary questions, and then difficulties will actually increase. So every tutorial same, we will start from the simple one. Then we will have the star question of the day. So this is the star question of the day, where we include the linearization. So when you have this, we will repeat everything the same. Introduce, deviation, variables, where we have H minus HS, Q Q minus QS, then no more. So then this equation will be ADH over dt Q minus 1 over 2 CHS. This is steady state value, so don't touch. Then HS. Then repeat Laplace transform both sides. Then you will getting AS HS bracket minus H0 QS minus, all of these are constant, so don't touch. And then this one, the S still not there. After your Laplace transform, only you will have HS. Okay, so initial condition will be 0. Then you rearrange, you will get your HS. Okay, so I'll copy this. We will try this one more time on Wednesday, using also apply numbers. So when you have learned in the lecture, I will expect tutorial you can derive this already. Okay. So once you have this, you'll be having AS, HS, move the output to one side. So 1 over 2 CHS negative 1 over the 2 HS equals to QS. Factorize your output. AS plus 1 over the 2 CHS negative 1 over the 2 QS. So output over the input, it will be 1 over AS plus 1 over the 2 CHS negative 1 over the 2. And compare this with K over tau S plus 1. Almost the end. You'll be dividing the whole equation with 1 over the 2 CHS negative 1 over the 2, 1 over the 2 CHS negative 1 over the 2, then 1 over the 2 CHS negative 1 over 2. Okay, then finally your K will be this, and your tau will be this, and this term will give you 1. That, yeah, that's right. Some of you follow my advice. I ask you to drop separation and just take control. It's not easy because of control involving too many maths. And now only week 2. We have more to go. Okay, so please do your revision before your tutorial. If not, your tutorial, you feel like you cannot follow. So if you do your revision already, you know how to derive the transfer function, then this is the week 2 content. We cover integration method. We cover the transfer function method. Then this will be the scope of your test 1. We'll be having more and more examples and also simulation. So I repeat, your Simulink, please install first. So when you install, don't forget to just install Simulink. The rest you can remove because there are many toolbox in the MATLAB. So you just tick the Simulink. Or you want to install the full package, fine. But please install, we are going to use the Simulink, I think week 5 and week 6 with examples. So we are not going to the lab to run the simulation. You make sure your laptop have the Simulink installed before week 5. So now only week 2. If you having any difficulty, cannot install, you go to ICT. Okay, so we are going to run the simulation soon. Week 5, you have few weeks to go. So now is to do the revision of this lecture, and then we'll be having our tutorial on Wednesday, 12 to 2. Okay, that's all for today. Thank you very much.